So I've got a couple of slides that we'll go through pretty quickly. Unfortunately, my co-presenter, Nirav Shah, was unable to be with us this morning from Intel, so I'm going to go through some of his slides, and then I'll spend the majority of the time, the meat of the time together on the main slides that I came to talk to you about. So this is just, this slide is meant to be a recap from last time. Last time, I believe, was probably the OCP Regional Summit in Lisbon. And so there's a number of factors that we're trying to talk about how these apply across the entire life cycle of a data center. And you know, there's these divisions into stages. They're somewhat subjective, but you could think of a plan and design phase. I prefer to call that an architectural phase. There's a procure your equipment, deploy it, and operate it, and then finally, when it's all done, when it no longer meets the data center's needs, you decommission it. And so in the middle column of factors, you can see various things that a network operator might want to consider as he's trying to operate this big investment we call a data center. And then on the far right column, you see a number of standards that are emerging, and it looks like there's hot links to these. But this is an update, a bit of an update from what we did in Lisbon, and I would encourage you, if you're interested in these topics, to go back and look at those slides. So there is again, my co-presenter was not able to be here, but there is a piece of work that he is championing, and it has to do with, I like to call it almost a design tool to design a data center. And so it would have a number of inputs. A prospective architect might enter various parameters, input parameters, and then this tool would go through calculations of power and cost and things like that, and spit out a design. And as I said, we're in very early concept with this. I don't have a whole lot to show you. Here are some of the ideas we had on the modeling parameters. You can see that some of these attributes, we're talking about scaling to a huge data center. And so some of these attributes, when they're additive, they're relatively easy. When they're non-additive, it's hard to aggregate them and sometimes and make some sense of them. I want to point out to you one particular row that's going to be a dominant theme throughout the rest of our talk, and that is the row on performance. And right now, the attribute is additive. But when we started the work that I'm going to describe for most of my talk, this was non-additive. And so what I've been trying to do is come up with a theoretical, solid math-based framework by which we could take performance of individual servers or units and aggregate them together to get some idea of the performance of a data center, and specifically the revenue expectation that a data center architect or a stakeholder, an investor, could reasonably assume from this collection of equipment. Just some more slides. Again, early concepts, some of the things that we would look at going into the resources required, cost, size, power, thermal, and then we get into things that don't add up, right? The vendors. And just some more ideas. Identifier, fault or error status, the health, the utilization of it, and the configuration of it. Okay, so I have a lot of slides to go through, and I have a script because I can't get through this material without the script. I'm not going to cover every word that's on the slide. You have the slides for your review. I would encourage you to look at them later. But what I want to do is I want to capture the highlights, the spirit of what we're doing, and hopefully I will capture the most important parts so that you can walk away with some comprehension of what we're trying to do. So in late spring of this year, we realized that organizing our approach to lifecycle around telemetry was a dead end, because useful telemetry is only present during the operational phase of a data center. The other limiting factor of telemetry is that telemetry schemas can quickly become unwieldy when they support different technologies, such as CPUs versus NICs versus storage. Our remedy for this situation is to leverage model-based systems engineering, or MBSE, you'll see that acronym a lot, to bring coherence across the different lifecycle phases of a data center. Practitioners of model-based approaches claim many benefits. A key one is illustrated here, is that the design knowledge, that's the gray curve on this slide, becomes available earlier to the architect, leading to better key architectural decisions and delayed cost commitments until after those better architectural decisions are made. A key activity of MBSE is evaluating proposals. For each proposed design, we want to express a utility, also known as performance, as a single number. And we also want to express costs as a single number. Translating performance and costs into single numbers can depend on the values and goals of an individual data center. For example, one data center might strive to reward a design's superior sustainability aspects. Another data center might prioritize longer service life. In order to better understand the design space, we plot each composing proposal as a single point on a two-dimensional plot graph, cost in the horizontal dimension and utility in the vertical dimension. The resulting visualization helps us understand what the possibilities are. Here's a look ahead. We use the horizontal axis to determine the data center's total costs, including initial equipment purchases and operating costs. We use the vertical axis to estimate the expected revenue from providing data center services. Then we can use standard analysis techniques to select the best proposals for meeting the data center's business goals. The first modeling challenge we run into is that different users want to run different kinds of applications. And different data centers may wish to target different segments of computer usage, depending on the data center's business goals. We attempt to categorize the universe of compute workloads into 6 distinct use case profiles: general compute, user interface, network attached storage, AI training, AI inference, and high performance computing. The performance versus cost trade-offs differ across these 6 profiles. So each of the targeted profile gets its own two-dimensional plot graph of utility versus cost that we saw in the previous slide. Obviously, we need a way to measure compute performance of a working system. The traditional answer is to use a benchmark test program. Now, the practice of benchmarking has seen many abuses over the years, and some equipment vendors resist the notion that compute performance can be fairly compared between competing vendors. However, we are encouraged by the rise of industry benchmark consortiums in which different vendors and purchasers specify how compute performance will be measured. Here are the key aspects we recommend regarding the specification, execution, and results publication of computer performance benchmarks. Number 1, the benchmarks must be relevant for the data center architects and operators. Number 2, benchmarks must employ broad credibility and use within the industry. Number 3, benchmarks must be created and maintained by consortiums of industry participants. Number 4, there must be strict submission rules and peer review of benchmark result claims. And number 5, benchmark results should be reproducible by others. Here are some examples of industry benchmark consortiums that we believe meet the criteria on the previous slide. For each of the 3 consortiums listed, we specify a list of benchmarking test suites that measure relevant data center workloads. Here, we map the various benchmarking test suites from the previous slide into the 6 use case profiles that we have already identified. Note that we have an additional column, virtualization, which is not a standalone use case profile, but instead can be an important cross-cutting aspect of the 6 use profiles. Also note that we have 2 use case profiles for which no benchmarking test suites are currently identified: user interface and high performance computing. The second modeling challenge we run into is that often performance measurements of individual compute units do not aggregate in a linear fashion. In other words, we can't take the performance measurements of each compute server in a data center and then simply add them together to arrive at the usable compute capacity of the entire data center. To tackle this challenge from the ground up, we define the notion of an additive performance unit, or APU, as I'll refer to it here, as a distinct set of IT equipment that can execute one or more independent sets of cooperating programs. And I've got a slide that unpacks those words a little bit more. We tie this APU concept into the business realm by assuming that customer usage of an APU can be valued independently as a revenue-generating asset for financial analysis, such as net present value, return on investment. Note here that the term revenue is also commonly used as a metric for financial analysis where the data center is providing IT services to other functional units within the same enterprise. In other words, your enterprise data center. In many cases, multiple users share an APU via virtualization, containers, batch processing, or some other sharing mechanism. Then we can express a data center's compute performance and potential revenue for a given use case profile by applying an aggregation algorithm. The trick here is that we don't attempt to directly aggregate compute performance. Instead, we aggregate revenue that results from each APU's compute performance. This slide shows the system definition of an APU. The APU is composed of various components. For example, processors, memory, non-volatile storage, internal interconnect fabrics, external network interfaces. Since the APU can execute cooperating computer programs, the APU can exercise and execute a benchmarking test in order to measure various aspects of its compute performance. The dashed red line in the figure delineates the APU from its operating environment. Power, environmental control, physical space are provided by the data center facility to the APU. A data center network is required to provide communication between the APU processing units and the rest of the data center. Optionally, external storage may be available to the program executing on the APU. Note that an APU is typically targeted to some subset of the use case profiles previously defined. Because of this, the definition of an APU can scale from a single host server to an AI cluster to a room-sized supercomputer. This slide is an exposition on the key ideas within the definition of an APU. And they're in italics for specific reasons that help us do the math of aggregating the performance of these APUs up to the data center level. The third modeling challenge that we have is to allow for the data center diversity in at least 3 dimensions. Number 1, different data centers will likely have different ideas about which of the 6 use case profiles to competitively offer to their respective customers. Number 2, within a given use case profile, different data centers will likely have different ideas about how to translate results of a benchmark's synthetic workload to the respective customer's actual workload. Let's remember, benchmarking, it's a canned program. Not every customer is going to run an instruction mix that mimics that synthetic workload. And so a data center may have different ideas about how faithfully to, or how literally to take that benchmark test. And finally, number 3, different data centers will likely have different ideas about the quantization of performance levels into discrete units for revenue purposes. And what I mean by that is we're going to have benchmarking scores for an APU, and we believe that in most cases that APU is going to be shared among multiple users through virtualization, as I said, or containers. So what's the minimum level of performance that a particular data center feels it can offer to a customer? We can support such data center diversity with the concept of a customized compute unit, or CU, which is a mathematical vector specified by the data center that allows it to normalize performance benchmarks with its own ideas about which service offerings are in the best interest of pursuing its own business goals. So where do these magical compute units come from? In practice, a data center would select a reference APU per profile, and through testing determine the maximum number of CUs, each of which provides some minimal viable level of performance to a user. So for instance, a data center could take an existing unit that it knows well, and it says, well, how many users can run the benchmarking test? How many users do we feel comfortable sharing this APU? And that's how we derive these compute units. The slide provides a rather abstract example of how a data center might derive a CU based on the benchmark results of a reference APU. I know that equation at the bottom might look a little scary to some. We're going to do a white paper, and we'll explain exactly what that equation means and how data centers can use that to basically estimate the number of users that it could provide service to on an APU that it's considering for purchase or deployment. Regarding network connectivity, we assume the data center's internal network connecting APUs is provisioned adequately to meet reasonable I/O expectations. We note that oversubscription of network links is a fact of life. The network requires careful design, and so data center architects will long have opportunities to work. For clusters, the private interconnect fabric can be sized to optimize the APU's benchmark score, and that's independent of the data center's internal network. Other network appliances, for example, gateway routers, load balancers, intrusion detection, should not prevent APUs from meeting expected performance. And you know what? I have it right. Optionally, a data center may offer access to additional storage devices being shared by multiple APUs. But remember, each APU includes adequate storage to run the relevant benchmark test. The use of external storage adds additional traffic to the data center's internal network, which must be considered by the data center's architects. The data center may choose to offer various tiers of external storage capacity and speed to users at apportioned costs of the shared resource. There likely exist multiple requirements that a data center imposes upon any APU under serious consideration for deployment. If an APU fails any one of these requirements, it is disqualified from further serious consideration by the data center architects. This slide provides examples of qualification versus disqualification criteria, and these will vary by data center policies. And so we finally arrive at an algorithm for aggregating estimated revenue across the entire data center. And I'm going to go through this slowly so we can hopefully digest it. Number one, we're going to create a tentative list of APUs for each offered use case profile. Number two, we're going to discard the lists of any APUs that fail the qualification criteria that we talked about on the previous slide. We have to determine the number of compute units yielded by each APU, and we did that with the equation I showed several slides ago. Remember that each compute unit, or CU, is the minimum level of performance offered to a customer. Number four, we want to estimate the potential revenue, ignoring volume discounting that the data center may be doing, for each APU. Remember that compute units could be valued differently depending on their use case profile, and so we have a relatively straightforward equation here. For each APU, if we take the number of compute units per APU, that's the number of simultaneous users, times the revenue per compute unit, we arrive at the revenue that a single APU could generate. Now it's time to add things up. For each offered use case profile, sum the potential revenue of all the APUs dedicated to a given use case profile. Number six, we combine the estimated APU revenue over all the offered use case profiles. Number seven, remember that external storage? We might be able to charge extra for it. Add in any estimated revenue from that. And then finally, there may be remaining revenue for financial purposes that we consider to add in here, like, for instance, equipment rebates, tax incentives, co-location arrangements, things like that. Next, we aggregate the estimated costs across the entire data center. This calculation is much easier than the revenue side because the costs are much more straightforward to model, I think. This slide shows the typical categories of costs associated with a data center. Cost estimates can be done at increasing levels of aggregation to make good decisions. For example, at the APU level, in order to make revenue cost trade-offs when evaluating APUs. At the use case profile level, to make revenue cost trade-offs when evaluating the optimum mix of use case profiles. And finally, at the data center, the highest level, in order to make revenue cost trade-offs at the data center level, plus confirm the financial viability of actually building and operating this data center. So far, most of my remarks have been in the context of predictive modeling during the architectural and design phases of a data center's life cycle. If we have good predictive models, then we can make better decisions before committing costs to a project of creating the data center. But as we move into the operational phase of the data center, actual telemetry measurements from running equipment take the center stage of manageability. This slide lists the most important categories of operational interest with a very brief categorization of how well these categories are currently supported by telemetry. And we acknowledge that there may be some difference of opinion in this area. But what I really want to get across with this slide is that there's much to be gained from comparing our predictive models from the architecture and design phases with the actual telemetry being generated during the operational phase of a data center's lifecycle. We can use this feedback to direct our focus on improving the current operations of the data center, as well as improving our predictive models for future evaluation of the data center and creation of new data centers. In summary, manageability of a data center across the different phases of its life cycle can be substantially improved by leveraging model-based system engineering techniques. This slide lists the most important benefits that such an approach could yield, starting when the data center is merely a future dream. Embracing a modeling approach has the potential to fundamentally improve how data centers offer services to their customers and how they select equipment needed to provide those services. I want to acknowledge and thank MIT for some illustrations that were used in this presentation. And finally, I want to invite the community to provide valuable feedback and participate with OCP in our quest to create a better data center. This slide lists specific ways in which you and your colleagues can help us. The URL at the bottom of the slide will take you to the root web page for the Cloud Service Model workstream, and on that root page, there's another link to our wiki page where you will find more details on the work that we're doing. Do we have time for any questions?
One question?
Time for one question. Anybody have a question? Going once? Going twice? Thank you very much for your attention.
All right, thank you.